Hello. Morning. Is this thing on? I think so. So hello and welcome. We're going to go ahead and begin. We're going to pick up where we left off before. Look to pick up where we left off before. And that is we were looking at this problem here. Guess number higher or lower. Also, happy Good Friday. See how far we get today with these problems. So we were looking at this yesterday, and I had something of a solution, but it was incorrect. But I think I can come up with another approach, which is basically we can let the left subtree be a subroutine. I think technically we can make the right subtree a subroutine also. Just thinking. Yeah, I could do like kind of a dynamic programming solution, I guess. It's probably quadratic time, which is basically memo-wise on the on a subarray or a consecutive subset. So start and ending indices are sort of the input keys to memo-wise on. Excuse me, I'll memo-wise on. I'm going to look to memo-wise on. Oh, you know what? There was a way to hash. I actually did learn that, a way to hash to write a hash function for an unordered map, so that way you don't actually need to memo-wise on a regular map, but you can memo-wise on a, what do they call that? On a hash map. Yeah, it's actually not that big of a deal after all. So you could use a pair of values as the inputs, or a tuple of values rather. Tempted to kind of code that up again just for the sake of like going through that exercise. I'm not gonna do that though. I'm just gonna use a map to memo-wise. But yeah, I want to say we could memo-wise, and what we're going to do. We don't need this library anymore, do we? We don't. Math library. What I'm looking to do is, let me just check something before we keep going. What I'm looking to do is, what's it saying? What I'm looking to do is so we'll have all of the sort of I don't know if that works though. The dynamic programming solution. I want to use a kind of recursive solution where we loop over all of the possible root nodes that we could use from left to right, and for each of those root nodes, we would then basically recurse on the left and right subtrees that are left, right, or left and right. What do they call that? Left and right. I guess possible trees that are left over. So this is sort of be generalized. The function that we're going to look at, the function that we're going to actually implement is going to be sort of generalized, the recursive portion. And yeah, you really just need a base case. I don't think you really need. I think it's fine, actually. I think this works. I don't think it's as hard as I'm making it out to be. I think this is perfectly fine. So, okay, so we'll do it this way. So, auto curse. I'll explain shortly what we're gonna do. Yeah, I don't think this needs to be that difficult. I don't know. I like kind of really struggled with this before. I don't know. Sometimes I have a hard time with questions that are like, I guess, dynamic programming questions, or questions that like you would expect to do them in a polynomial time, but not like linear or log linear, or n log n time. So all right, so we'll say start index, end index, and we're going to say base case. So Okay. Well, so I want to say something like, there might be actually multiple functions we're going to use here. Helper. Do it this way. Helper. Start index is greater than end index. Return 0. Start index is equal to end index. Return start index. All right, the value. Actually, that's just 0 also. Just thinking, what are the base cases to work with here? Basically, what we want to do is, the basic idea is pick a root, split the range into 2 pieces, operate on those 2 pieces, and get the maximum. Yeah, so let's actually do that. Root. In that case, okay, let me try again. So have a root value. Select a root value. You have a left and a right. You break into 2 subcases, the left and right subcases, and you're going to say add. With the solution on the left subcase and the solution on the right subcase, it's the. I guess it's, yeah, we'll just call it the solution to those cases. Kind of making it kind of deliberately vague and abstract, but to kind of describe in more detail would be like what of all the possible arrangements of those particular subtrees, the one that would give you, in the worst case for that subtree, the smallest worst case value. That's what we're looking for, right? And we're going to take the left subtree, we're going to take the right subtree, and we're going to compare, because you have to, we're taking the path, right? So it's the smallest worst possible path through that subtree. That's kind of what we're looking to do to a leaf node. We want to add the root value to that, so we want to return the root. Really, you would return the root here. You would root plus the left side, root plus the right side. However, what's interesting about this is there's some recursion here, in that you're going to, in order to figure that out, if you don't already know it, like if you already knew the left side and the right side, right, it's just the start index and the end index. If you already knew what that was, then you would just return that, right? You do exactly as just described, the left solution and the right solution, and you would just compare. Really, it would be both of those plus the root value. So it would just be the return value you're looking for is the root value plus the smaller of those 2, or the larger of those 2. And now what's interesting about that is that's it. That's what your function would do. Now the tricky thing is, right, so this is very tricky, isn't it? I kind of want to break this into different pieces somehow. Because really it is, you don't actually pick a root just yet. You would do something like this. So, okay, that's confusing, but all right, let's do it this way. So, base cases. If start index is greater than end index, return 0. If start index is equal to end index, I want to say you would just return 0 here, right? Because if this tree was just one node, like your guess is just right there, right? And now we're gonna say for int I equals start index, I is equal less than or equal to end index plus I. Now we're gonna select the different root nodes, right? And we're going to say ret 0, and we actually want to minimize the other way around. We want to say forgot to use standard put money. What's up, Yuki? Welcome back. Hello. Welcome. Happy Friday. It's Good Friday, man. Welcome. Forgot to use standard put money. Yeah. Standard get money. Actually, I think that's a function. Something like that. Let me see. There's like a money function thing. Yeah. Money get do get. Contest server. Oh no. Did I get hacked? Did I make a mistake? Contest server CS. Facet category. I was like, that doesn't look like the locale money get. Yeah. It's the CPRF locale money locale. Hold on. Money put. There you go. Yeah, the money put function. It's real. Ever used get money? You need to swap to Google ASAP? No, sir. I'm rebelling against put money. Oh, you're right. There it is. Put money. Whoa. Wait, Yuki, how do you? I thought I'm so confused. I don't know you that well, like personally. But you give me the impression like you're a software developer. Blows my mind because I'm like, how do you know that? How does he know the put money command? Where did that come from? Why would he know that? I don't know what the word is. I don't want to say I'm shocked, but I'm just surprised. I'm a baller. Yeah, you were talking about the only reason I even know that exists is because like over years of just messing around with stuff, I eventually bumped into C++ locales, and I was like, oh, there's a money function. Like, oh, that's weird. What do you do professionally? Like, what? Like, I'm so confused because I'm like, how does he know that? Because I think the other day you were talking about doing C#, tinkering with C#. I don't know, was it C# or was it something else? So .NET maybe? I forgot what it was. It was some .NET thing, and it was like a GUI kind of a tool. And I was like, oh, I thought like I was under the impression that you were not a software developer. So I'm just like can't process, I'm like I don't know I don't know enough about you to like really say one way or the other like what to expect, because this is the internet, like anybody could be anything basically. Like I've run into people who are like on a whole different level. There was a guy a while back who is a PhD in combinatorial mathematics, something like that, or specialized in combinatorial mathematics, and I was studying I was tinkering with like difficult counting problems, and so he would come in like just like what do they call that? He would come in, as the kids would say, he would come in hot and be like, oh yeah, I solved this problem, or oh yeah, I did this, I tried that, and it's like, oh yeah, you could try this, and I would just be like, what? Like, where made you think of that? Like, what? It's like, oh, well, I'm a PhD specializing in combinatorial math, basically counting. And it was like, oh, that's why. It's like freaking just, Yeah, you don't know who you're talking to sometimes. It's just very like, it's fun, but it's pretty wild. It's like, yeah. But anyway. C# forms. That's what it was, right? Yeah. .NET C#. Right. Simple as like dragging a button onto a window. Oh, okay. Yeah. Fair enough. Yeah, I don't know. I don't know. I don't want to say like you never know what other people know. If that makes sense. Like you can't know. Yeah, you can't know someone else what. It's not that you can't know something. I'm not trying to say that. I'm trying to say you can never know what is inside of another person's mind. If that makes sense. So like I don't know. If like and again I don't. Okay. And also I'll say I don't know very much about C# forms. So like just not knowing anything about it, it's already like, I'm like, oh, what's going on over there? He's got a skill that I don't have. Wow. But basically, all right. So what was I saying? So what I wanted to do was call this. So I want this to be recursive, and we're going to call this recursively on the left side, the right side. So now that's a question. Val is going to be, we said it's going to be I plus val, and the recursive function is going to be as follows. So the start index, it's going to be, start index to I, and the other one is I to end index, and actually you're not going to include I. See, that's the thing, I minus 1, I plus 1, and there's a tricky thing here where, we said, if the start index is greater than the end index, then we just return 0, so that shouldn't matter. We want the larger of the two, right? So we have 0, so we don't need to get too crazy about like edge cases where the start index is greater than like I minus 1 is a negative value or something like that. We don't have to worry about that. Taking the larger of these two. Is that right? So we're taking the larger, and then red is going to be I plus the larger of those two. And okay, and then return red. Oops. Something like this. So I think if we do this, I want to say this will give us what we're after. I want to say this will give us what we're after. I think you could literally do this. Start index 0, end index n, curse. What does this do? Let's just do that. What does this do? Excuse me. Compiler error. Nice. Perfect. Google Image UI. C# is better than Java. Is the better Java? Yeah, I don't know. I don't like Oracle, and I don't like Windows. With Microsoft, I don't like either of those companies. Oracle's not as bad as Microsoft though. It comes to like the social impact and like the damage. But yeah, I don't really prefer Java nor prefer C#. I like C++, as you can tell. I like because C++ has an open source compiler. It's a GCC compiler. If you want to program for Windows, you do need to use MSVC, but you don't have to program for Windows. You can run your servers on Linux if you want, and you can write software for Linux if you want. So I appreciate that. I like having kind of like a degree of separation from corporate interests. Now the tricky thing though is that like all open source projects are usually funded somewhere by somebody, so it's not like, even though it's free and open source, it's not like totally washed of blood, if that makes sense. There's sort of like still blood on your hands even if you use these other, I'm referring to like ethical consumerism, right? If I don't want to support companies that are doing questionable things, so would not want to use their products. And you might be wondering like, why are you talking about blood in software? Well, the reason is So like China right now has Uyghurs in camps being like murdered and raped. Basically, they have like, they're basically just like, they basically have like the Holocaust, but probably even worse right now in China. And as far as I know, like Microsoft, Google, like a lot of these big tech companies, Amazon, they do a lot of, they're very chummy with China in terms of their business partnerships. And I guess the way I would express it is like, we outlawed slavery in our country so that way we would stop using slave labor and using slaves. And it's like these companies are like, yeah, so we'll just go to another company that has slaves. Go to another country that has slaves. Like, just because you outlawed it here doesn't mean we can't do business with them over there and use their slaves. It's like, right, so, okay. That's not right. So I'm trying to not do business with those companies as much as I can. However, they're so pervasive in our culture and like who I am as a person and the sort of things that I do day to day and like the products and whatnot. It's like very difficult for me to really pull away from all of that. Sorry, I realize it's like a lot of like, there's a lot of connections there, but basically I'm trying to avoid using big tech products because of their relationship with China and other less than reputable countries around the world. And yeah, so one of those things is like, well, if you use open source software that's free, you're not like directly supporting these companies. And unfortunately, Linux itself is funded by corporate interests anyway. So it's like, you can't really completely get away from it all. But I mean, you're not like, I don't know how to say it, because like even, yeah, it's hard, because even if you use stuff that's open source, like open source things still need to be maintained. So like you still need to have support, and the support has to come from somewhere. So even if it's free while you're using it, like you can't use it forever for free, if that makes sense. Somebody has to pay for it to update things and change things and add things and remove things and all that. And time is money, right? So like it can't be free. So anyway, I'm kind of rambling on now about software and how it gets funded and all that, but really the complaint is kind of meaningless to begin with, because like I'm in the world, I'm a Christian in the world, not of the world, and there's no way to really get around that. It's like you're gonna, God made the world a certain way and made man a certain way. You can't make people not be evil, right? Like you're gonna be dealing with evil people no matter what. You don't necessarily, as long as you're not explicitly doing something evil. And if it's like really obvious, like for instance, like Volkswagen is like really chummy with China, it's like I probably shouldn't buy Volkswagen cars. Like I have a Volkswagen. I'm like not gonna buy it. I'm not gonna buy I was gonna buy the car at the end of the lease, but I don't want to buy it now because of going to buy it at the end of the lease, but I'm not going to do it now because I realized how close they are with China and what China is doing to their people. It's like really, really sad. Yeah, I'm rambling. Now let me get back to the problem. Forgive me. So, okay. This should be fine. What's wrong here? Wait, what? Oh, yeah, what? Actually, that's not maximum, it's minimum. By the way. Overflow. Oh, no kidding. Oh, yeah, that's why it overflowed. Okay, that's confusing. The reason it overflowed is because of because I used a maximum here, and then this value would return this maximum. This would always return this value, and so this value would be the largest int max, and then you do I plus that value. So in like two steps, you'd end up overflowing. Yeah, that was confusing. But yeah, I made a mistake. It should have been a minimum. That's why you make this a maximum, because you're trying to minimize. Yeah, that's confusing. So, all right. Let's see. How we do here? I was trying to do something kind of fancy before, but you don't need to. Keep it simple, you know. Let's just try this. See how this goes. I think these are going to TLE. I don't think those are going to complete. Because this, I think, yeah, this is, I think this is exponential time. This one, before, without memoizing it. Yeah, it's really expensive. Let's go up to like 12. Alright, pretty good on 12. It's kind of like a brute force solution. Not really, I don't know. I don't even know what the runtime is. It doesn't really matter. If n is only 200, you can kind of make this pretty inefficient. It looks like it's correct though, which is good. It's kind of what I was hoping for. Hoping it would be right. How do we do? 26 minutes. Ouch. Alright, TLE. Okay. Now we're gonna memorize. I'm not gonna use the hash map shenanigans that I was describing before. I'm just gonna use a regular map. So I can do int. It's gonna be a map of standard tuple of ints to an int. It's gonna be memo, and then we're gonna say base cases if memo dot count of standard make tuple of start index and index. We can do key just say memo of key ret. Okay, how does this go? How does this work? Is this thing on? There we go. That's a lot faster. All right, let's go to like 100 and 200. See how we do. It might still TLE. Oh, there we go. Okay, it doesn't. I think we'd be fairly confident that's correct. No! You kidding me? What is this? No! What? Come on. Really? Oh, are you kidding? What? It passes the test cases, but it doesn't pass the... Come on, man. That's upsetting. No. Oh, really? I'm kind of surprised. This isn't really that inefficient. This is like relatively efficient. It's not that bad. It's really not that bad. This should be okay. I don't know. It's not okay though. For some reason, it's not okay. Some reason, it's not okay. Now we could do a couple things. I don't know if that. Yeah, you know what we're gonna do? There's an optimization that we could do also, which is kind of fun. So we can make this static. We do that. That'll be a lot more efficient, I think. So yeah. Yeah, if you make this static, it's more efficient because basically all the subroutines that you call end up being you don't have to call them over and over again, I guess, if that makes sense. You know, I don't know, man, I'm afraid to hit this button again. I'm afraid to hit submit again. It's not that much faster, is it? Just thinking, how could I make this? Shoot. Let's go 4, 3, 2, 1, 0. 89. Oops. Whoa. 88. 87. Just thinking, if you can get the test case to TLE. All right, how's this? How do we do? We submit this. I don't know what's gonna happen. Oh, okay. Hackermans. We got there. All right. Hey. Okay. Well, I think the reason why this is so inefficient is it's cubic, I want to say. That's pretty funny. Yeah, 8 million. I want to say this is cubic instead of quadratic. If it's only quadratic, it should be like super efficient. It should really not be a problem at all. I think it's because it's quadratic. Or cubic, rather. I didn't really think about that. I don't know. For some reason, it seemed like this is just not cubic. Well, because my thinking is that it's. I don't actually know what the runtime analysis for this is. I didn't really do it. Yeah, two slight optimizations, and basically this is like pretty much a brute force solution. Like this is kind of just a brute force solution with a couple of optimizations. One optimization to memoize, and then a second optimization to memoize to remember your solutions between executions, because these are, because these are, what do you call it? These kind of build on each other, each solution when you compute it. So you don't really need what do you call that? You can save your previous calculations like across multiple function calls, which is what happens when we make it static. Which is where we get that little extra speed boost, which gets us in range to not time out. Wow. Now, okay, great. Now here's the thing about this question. This question is great. However, more likely than not, there's probably more to it, more to think about, more to talk about here, where you probably could do this much faster, because this is kind of like a maths counting kind of a question. There's probably a way to either optimize or, compute in like a little bit more, a more clever way, a smarter way. Almost certainly there's something like that involved here. I'm definitely kind of sad that I TLE'd on the first shot, and then I also was really not very efficient. I didn't do the analysis though, which I probably should have done, which would be basically, because you have two parameters and you have a loop inside, this memoize function memoize over these two alternating parameters, and this loop in the interior should be cubic time, which is n cubed, O of n cubed, which is pretty inefficient actually, all things considered. Even for 200 elements, it's still pretty inefficient. Yeah, that I really basically you loop over these elements from 1 to n, you loop over these elements from 1 to n, so that gives you quadratic, and then memoized. Actually, this memoization makes it you get a logarithmic term in there too, so it's technically an n cubed log n, O of n cubed log n. But yeah, this extra loop makes it an extra linear term as well. So this is 2 linear terms here and a linear term there. So 3 linear terms, which gives you O of n cubed. I think that's the way, the sort of quick and dirty way to kind of determine how this is, what the runtime would be for this. So that I should have known. I should have caught that. I don't know why I didn't see that and realize that. I don't know. I kind of forget sometimes. It's kind of a really basic thing, but I tend to forget that. So yeah, I mean, we could just move on, but I think there's definitely some like fruit to this question in that we could find, probably the discussion will have more stuff about like optimizations. I'm definitely kind of sad that I ended up just doing that. Like this is kind of how it goes for me with a lot of problems, where I just kind of like, you kind of have to let go a little bit, just give up on trying to find something like super efficient, and just find something good enough, and start with that, and then think about possible ways to kind of optimize. But you really you want to solve the problem first. Like that's the thing. Try to find a solution that's inefficient, and then try to find a solution that's slightly more efficient. Like, because the first solution to this that's inefficient would be if we didn't memoize this at all, right? It was just really just brute force, right? We just check every possible root node that you could have, and then basically recurse on the two, consider the 2 subtrees, recurse on the 2 subtrees that are left over on the left and right side, and then given that root, you can figure out what value you would get for the minimum path given those 2 different roots. The minimum path given, not the minimum path, the maximum path given those 2 different subtrees. What the maximum path is for those 2 subtrees, and then you can, of all of those roots, you can take the minimum possible, right? So like this is actually pretty simple logic here. But then the issue is, yeah, that's really it. And it's recursive, right? So it's like kind of a brute force thing, is that you just kind of try for every root, every possible root, and then sort of recurse on the 2 subtrees. And then the optimization is that, so that would be exponential time if we did it that way without any memoization at all. And then when you memoize, it becomes polynomial time, becomes cubic time, and in this case. And then we can actually memoize across function calls, by making the memo function, making it static. And we could have actually defined our own hash function to make this an unordered map, so that way it would be cubic, expected time cubic, rather than or amortized cubic rather than cubic log n, which is what it is right now, or O of n cubed times log n. So yeah, I mean that's fine, and that was enough for this problem. I mean they put the range of values for n small enough so that this would be sufficient. Now a couple of things to say. I would say, one, you probably could make this more efficient than that, and it probably doesn't have to be n of 200. It could probably be much larger values of n. And the other thing is they have hard difficulty problems on this website. I've noticed some of the hard difficulty problems are just advanced versions of the same questions. So they might ask, so you see how there's a 2 here? There probably is a question that's a 3, and they would say, basically unbound n, or make the bounds for n the constraints for n a lot harder. And that's probably this solution wouldn't work in that case anymore, and you probably have to go to the discussion to see, not the discussion, but you'd have to think about it to figure out a way to do this more efficiently, more cleverly, which is kind of what I want to do now. It's probably going to be there in the discussion. It'll probably kind of ruin it a little bit, but I just want to think how, if we could get rid of this inner loop, that would make things a lot more efficient. Excuse me. You kind of can. I would actually say go with the ending index, and let's do it the other way. This is actually the idea that I had before. I was trying to kind of articulate it, that you could actually make this write this loop slightly differently, where you kind of know you kind of know that the node you're looking for is going to be on the right side, and so you can actually start from the right and go right to left. And if you do it that way, it's a little bit better. And we're going to say there's this value, right? And we say if so we're going to have int next val or next possible. It's going to be I plus value. So we say if if next possible is less than what we're currently looking at, or update ret to next possible and continue. Otherwise, we're going to terminate early, we're going to break. So this, I think, is a little bit more efficient. And I'm hoping it's still correct. It's not still correct. Okay, great. Nice. And what did I do? Wait a second. We're going to go backwards now. Okay, wrong. Nice. Interesting, 9. Huh. Is that not... Hold on. Really? Okay. Alright, never mind. My idea before, I think, was not really totally correct. So this probably we could finish the word here. Pos is kind of a weird word, right? Next pos. I don't know if that's a great variable name, particularly good variable name. I want to say I guess I'm wrong about this. I guess I'm wrong. I was thinking basically that idea that I had before of like the root that you choose, the root value of the tree, you would start sort of the largest number and then go from right to left to find the which root is sort of better. And actually, it's not really clear. It's not really clear. Excuse me, I was thinking was that. My thinking was that you would jump a certain number of roots to the left. So I think I actually had the right idea. It's just it's not a linear jump that we're going to do here. It's actually it's based off of the size of the subtree that we're going to jump. I guess what I'm trying to say is that this loop could be made to be logarithmic rather than linear, and then we have O of n squared times log n squared, because O of n squared times log n, which is a lot more efficient. Yeah, I want to say this outer loop could be made logarithmic rather than linear. This loop, which would make the algorithm a lot faster altogether. Excuse me. The question then is how do we do that? We kind of hinted at it, alluded to it before with, we had sort of like, let's say we did 1 through 10. We had 7, and there would be 9, 8, and 10 here. And then this part is just sort of recursive. Just put a big R in there, and it's just recursive case. what I want to say is basically if you had like 1 through 20, yeah, 1 through 19 and 1 through 20, these two cases were interesting because 1 through 19 you would do kind of business as usual where you'd say 18, 17, and 19 as such, right? And then 16 would go here, and then everything to the left would be the recursive case you don't worry about. And your values would be, I think 15 was 15 here? Yeah, we do 15. Well, all right. What is the number for 15? It was an interesting spot because '15 has 30 here, right? So this is for 19. 30, you could do 30 and 16, and this is also 16 and 18 is 34, right? So this will give you 46 versus 34. 46 works, but this also gives you, whoops. This also gives you, there's another possibility of 18, 19, 17, and 16. No, not 16. Does it work? How does this work? It's, I think it is. I think it is 16. But then we could put something here, which is not 16. I'm sorry. No. What am I doing? We want to put 6 nodes on the right, or we put 7 nodes on the right side. 7 nodes are 19, 18. And forgive my chicken scratch here. 19, 18, 17, 1, 2, 3, 4, 5, 6. Put these 7 nodes on the right side. So the root node is going to be in the middle of this, which I think is 17. No, 16. Yeah, it is 16. On the left side, right. I'm sorry, I had it right the first time. Okay, so on the left side is 16. On the right is 18, 17, 19. And on the left side you have 15, 14, 13. So 14, 15, and 13. Okay. So if you do this, this is the other way of looking at 19. And then this has a parent node, right, of 12. And then this is recursive 11, right? So my point, and this is a very long-winded point at this juncture, is that you could have one more level above 16, right? Fill out all of these nodes, and then have the recursive value here for 11, which is, I'll explain why this is meaningful, relevant here. 18 on the left side. So this gives you 18 on the left side. So 18 plus 12 is 30, and this is wrong though, what I'm doing. This is actually incorrect. Why do I think 19 was the one to do it on? I don't think it was 19, I think I'm wrong. Maybe it was 18. Hold on, I don't remember. I think it was 46 was the number that I was looking at the other day. Oh no, it was 19. Yeah. What? I'm doing something wrong here. I'm doing something wrong here. Oh no, no, we're fine. No, I'm sorry. No, this is right. No, we're good. This is 30 versus 34 plus 12 is 46. No, we're right. We're fine. So my point. Sorry, I'm confusing myself. We could do 30 and 46 with one extra node on top, where 46 is the number that we're going to get, right, the maximum. Or we could put 16 on top and still get 46. The point being, you could rearrange this tree in two different ways, and you'll still get the same worst case, right? What that means is, if it's better to put this node on top, right? If this number was 45, then you would actually want to go with this route rather than just 3 elements here. You would want to have a full tree over here of 7 elements. So the point is that there's like triangular numbers, I guess, or not triangular numbers, but numbers representing a full right subtree that you may want to consider, and that would those are exponential hops. And if you do make those hops, so this is sort of a representation of that. Like, this is basically selecting what root we're going to have at the top. You can actually skip a lot of the numbers and just do sort of exponential jumps to get to a better possible root. Still doing this sort of recursively. And actually, you can even do better than that, because I think you can make this even better than n squared log n. If we were to use hash maps, memoized hash maps, you can do even better than that, because you don't really need the right side to be memoized. You really only need to care about memoizing the left side. And the left, because the right side is almost not a consideration, right? The right side is literally just these 3 largest values, right? It's always just going to be those 3 largest those largest values. So it's actually going to be the sort of the exponential hops that you make. You can kind of add those up, and that's always going to be that's probably always going to be the answer too. But you just have to compare that against the recursive solution, right? The recursive part added to the head node. So that would actually give you, I think, something at like n log n time, which is pretty good. That's kind of what I was alluding to yesterday. It was kind of challenging for me to fully express it, but that's kind of what I was getting at. I think I have a better handle on it now. Yeah, I think that's a solution to this problem. And I would be willing to bet that would come up in the discussion, and I'll give this a plus because I like this question. And there's probably a third question here, and with just a larger constraint, larger number for the constraint, and that's probably a solution to that problem. So that's probably how you would solve this hard version of this problem. Let me try to implement that though. What this would look like is something like the following. You have basically a few different options. You have full trees on the right. That's pretty much what you're going to look for. Full right nodes, or yeah, right. Full binary search trees on the right. And so you're gonna have 1, 3, 7. I think it's going to be, it's 2 raised to the n, or 2 raised to the x rather, minus 1. Right. So this is, it's 0, 1, 3, 7, 15, and so on. Right. This is 2 raised to the first is 2. 2 raised to the 0 is 1 minus 1 is 0. Right. Those are sort of the numbers that we're going to consider. This is yeah, looks something like this. So let's try to code that up. Let's comment this out because we don't want to lose this, but we do want to hold on to it. We do want to modify it. Okay, so I don't know, P2 we'll call it. It's power of 2, and we're going to start off at 1. And we're going to say I is going to be equal to, so to start at the end index while we're greater than or equal to the start index, I'm going to say I is going to update to itself minus this P2 minus 1 plus 1. it's really oops, that wasn't what I wanted to do, but okay. It's really P2 minus 1. We're gonna leave that in there. And P2 at each step is going to, it's going to be equal to, it's going to bit shift to the left 1 bit. Right, so you're going to multiply it by 2. It's a power of 2. Right, and yeah, we update I that way. So let's try this. Let's see how this goes. Wrong answer. No. No. Shoot. It's not I equals. I is going to be equal to N. It's not, yeah, it's N. Is it N? Am I doing this wrong? Oh, yeah, that's wrong. That's not right. You could still do, this has to change, actually. I need to modify this. There's 2 things that need to change. It's got to be, I do think it's N. I think it's still N. It's just this part changes as well. I do think it's still N. But we do end up with something here, which is, oh, okay. It's the sort of the right, what do you call that? How are these numbers related to each other? It's this sum down the right side that we're looking for. That's going to be the other piece that we're going to compare to. This is only a difference of 1 number. This is a difference of 4 numbers. So really, it's like, how do you express that sum? That's like, you can call it the right sum, I guess. And it's going to be n minus 0 plus n minus 1 plus n minus 3 n minus 0 plus n minus 1 plus n minus 3 plus n minus 7. Yeah, that's the sum. So this is, we can compute that sum as well. And then we actually don't add this one, so it's just these numbers. So we'll say int right and left. It's recursive. And really the start index doesn't matter anymore, right? This could always just be, we could actually remove that later when we can show this works. The right side is going to be 0 for actually, it depends on what, yeah, we could do. Count to 0. Okay, so the right side, initially, if we're at the end index, we make that the root node. The right side will be 0, right? It's going to be 4 int x equals count x greater than or equal to 0, or greater than 0, minus x. So we do this count number of times, and we're going to write plus equals temp, we'll call that 1. So temp is going to bit shift to the right 1, or bit shift to the left 1. So multiply by power of 2. And then right is going to be n minus temp should start off at 2, I think. Temp minus 1. That's a little confusing. Yeah, n minus 1. So start off at 2, 2 minus 1 is 1, n minus 1, then 2 becomes 4, minus 1 is 3, minus 3, right, so we add all those numbers, that's the right side. We increment, we multiply by 2 on temp. So this is kind of confusing, what's going on here, but hopefully that makes some sense. So we get the right side, we get the left side, and now we say this value is the maximum of the left and the right. And then our next possible is going to be this I plus this value, next possible. And we also are modifying for each I. We're saying this is going to be P2 minus 1, and is P2 minus 1. Yeah. So something like this is what we want. Now, this doesn't quite work exactly as we want, because this n is really end index. So I don't know, just call this alpha. Running out of letters to use. It's not really n here, it's alpha. Does this make sense? No. It's close. It's really close, but not quite right. So what happens to the first 5 elements? The 5 trees. Output 2, expected 1. Okay, so we're looking at 2, a value of 2. What happens? 0, 2, right? Oh, this should be a 1, shouldn't it? Just by the way. Totally not sure if that matters or not. Okay. I think I have the right idea, just don't quite have the implementation correct yet. Ooh, excuse me. Okay. Maybe there's something in here that I'm missing. So for maybe I'm missing something here. So we're looking for. That's so much easier, just brute force. So much easier. What are we looking for? Excuse me. All right, so let's look at some of the test cases that it fails on and see if we can figure out what's wrong. So for 2, we expected 1, but we get 2. For 2, 1, 2, we expect 1, but get 2. Now, why is that? Okay, well. Excuse me. Excuse me. So call this on 1, 2. So 1, 2. Pass through all that. I is 2. 1. This is 1. Alpha is 2. Okay. Right's up there, right 0, and temp is 2, so we calculate the right subtree, I guess. Now, this value should be the count is 0, right is just 0, which is true, right? The right side is just 0. And the left side, start index of, oh, that's interesting. No, see, that's not true. No, that's fine. This should be 0. This should return 0, right? Start index is 1. I minus 1 is 1, right? This 2. I starts off at this end index of 2. So this should be 0. So right should be 0, left should be 0. And set this value to be 0, I plus 0, y is 1, next possible less than ret, which it is. So we have ret set properly. Okay, so we should just return there. Now, I think what happens is we have P2 gets updated, so we said alpha is 2, end index is 2, I is 1, and start index is 1. P2 goes to 2, it shifts to left, 1 goes to 2. I goes to 2 minus 1 is 1, alpha minus 1 is 1, I is 1. Wrong. This should go... Excuse me. No, this is wrong. I think I see the problem. We can keep going, but if it doesn't improve, then it's not better. But this, we're really kind of done here, right? Basically, we selected 1 to be the root. I is actually initially, you start off at P2 minus 1, I want to say. And then, so P2 really should start off at 2. That's kind of what we're saying here. Yeah. Pretty much. Something like that. I don't know. Oh, that's right. No kidding. Really? Am I just correct? Wow. Really? There we go. Because I'm a genius. See that? It's because, oh! Immediately eat those words. Curb your pride. Curb that pride. Genius what? Genius what? What do you mean genius? Alright, what? What? Never mind. Ain't nothing. Maybe not. Maybe not. Maybe not. Maybe not. Oh, you're kidding. Wow. That was bold. That was bold. I was very wrong. Oh, a lot of these are wrong. Oh boy. Oh. Ouch. Okay. Yeah, a lot of these before 200 are wrong. Whoops. Whoops. There you go, Will. Overconfidence. Overconfidence. Wrong. Alrighty. Wow. That's rough. That's rough. Seems like they're all wrong. Start with the first one. 130. Should have used a larger test case before I submitted it. That was bad. That was a mistake. So 593 expected 585. So I guess. What I want to do is I want to find a test case where this fails on that's relatively small, right? Like, is there something between like 20 and 100 that I can find? There's got to be something here where this stuff's working properly. Do I really have to go all the way? I think this works until I go to the next sort of, we start messing around with more levels on the nodes. I think basically past 128 is what I'm trying to say. Once there's once there are more levels to consider. Still works, but once we get to, I think once we get to 127, 128, I think that's where things start to get questionable. All right, let's do 126. Let's test this hypothesis here. So close we get. Wrong answer. Okay. Which ones are wrong? Okay. Yeah, looks like 124, 123. Okay, the bottom three. All right, so 124, 125, 126. That is, those are all wrong. Why? It's a little too high. What happens with 124? So 124 is kind of involved. 1 to 124. There are a few possibilities, right? We could do 124 down here, and then 123 up here, and this recursion on 122. That's one possibility. There's 123, 124, 122. Maybe I just programmed this wrong. I don't know. Could have just coded it wrong. The algorithm might still be correct. That's kind of what I want to test to see if the algorithm is still correct. 121, and then recursion on 120. So we do need to calculate each of these things, I guess. And there's, we said 7 of these nodes. 121. And then 3 nodes on the left side, which is 119, 118, 120. And forgive me, I'm getting a little sloppy here because I kind of just want to do it quickly. 124, 122, 123. Right? And then we get 117. And recursion on 116. All right, these are all sort of the optimal possible root values. Now, this seems to work reasonably well up to a point. Why does it fail though? So it fails at 124. So what are these? There's more. This is sort of n minus 2 to the first minus 1 is 123. N minus 2 to the second minus 1, so that's 3. N minus 3 is 121. Actually, it's minus 1 is what we're supposed to recurse on. Subtract 1 to recurse on that, but I'm not sure if that really matters. I think we do that correctly, but anyway. Okay. Then this is 2 cubed. 8 minus 1 and minus 7 is 117, right? Minus 24. Yeah, and then we want to do n minus 2 the fourth minus 1. 16, 15 is 124 minus 15 is 109, I think. So we have 109 and recurse on 108. So we have 109 as the root. And then a bunch of stuff on the right side. Then we have 2 to the 5th minus 1 is 31. 2 to the 6th is 63. right? 120. Okay, and this is the next one is 2 to the 7th minus 1 is 128, 127. Okay, so this one doesn't work, right? That one we should end up in kind of la la land, I guess. Yeah. Now I'm wondering a couple of things. Excuse me. If we're calculating each point, the right subtree correctly and the left subtree correctly, so doing this by hand, what we should end up. Basically, I'm just checking this test case to see if I think I probably made a mistake somewhere in my code. I'm just checking this test case to see that the algorithm actually follows. First off, if the algorithm by hand gets us the right answer, and second, if my code, if that's true, then my code needs to be fixed because it doesn't follow the algorithm exactly. So to get the value that we're looking for, which is 555. Do any of these possibilities get us 555? That's the question. So each of these are going to be, this is 124 minus 31, which is 120 minus 30 is 90, 94 minus 3, or 90 minus 1 rather is 3, so it's 93 is the root node. This is 124 minus 63. 61. The root node is 61. So this is, the root node is 61, 63 nodes on the right side, and then the recursion is going to be the difference between, right, the recursion is going to be 62, it's one less. Recurse on 62, recurse on, or excuse me, 60, actually, yeah, it's one less than this. And this recursion is 92. Okay. So we have 60, 92, 108, 116. All right, so we want to get the recursion for each of these. So we can do this by hand. So we're just gonna get another one of these going. And we said so 123 is the important one. Each of these recursive cases will compute directly. 122, 120, we can record them here, I think. $116, 108, 92, and 60. Okay, so we want all of these. We want each of these now. Okay, oh no, we're fine. That's good. All right, great. So are these all correct? Let's start with that. Oh, no kidding. 124 is the one that breaks. All correct up until that point, right? Yeah, very interesting. Yes, yeah, 124, yeah, 123, okay, great, perfect. We don't really need to care about 123, we care about 122, 120, all these other ones. We can get rid of 123, I think, actually. We should probably just remove 123 altogether. Don't care about 123. Okay. So now we have the right list of numbers. So our recursion for those pieces are fine, which is great. Excuse me. Oh. The issue is we want to compare those values to So there's the recursion plus the root, right? If we do compute each of those plus the root, let's do that sort of in one shot. Those are all the left subtree values. All right. So plus 122, plus 120, plus 116, plus, is that right? 116? Did I get that wrong? That's really close. Yeah, it's 116. It's plus 117, rather. 121, 117, 109, plus 193, plus 61, right? All of these numbers are 666, oh boy, no kidding, yikes, 6450, 618, 548 plus 9 is 57, 557, right, it's very close. This is the number that we got before, I think. And this is 4, interesting, 490 plus 350 is 440, 448. And this is 275. Okay, now I think this is wrong. I think we could have picked a better value than 109. I want to say that's the issue. Is that you could have maybe manipulated the numbers a little bit. Instead of getting 557, but get 555. Yeah, that seems to be the problem. Oh boy. Oh, excuse me. Yeah. 557, huh? Right. That's interesting. Because what we end up doing is we pick the maximum. In each of these cases, we pick the maximum of the left side, so that's the left subtree calculated, and then the right subtree. And the right subtree calculation is really simple. Sort of as described, the right subtree is you kind of just go down the largest path, or down the rightmost path. And yeah, so the right subtree in each of these cases ends up being I think my algorithm was I think my calculations were correct. In other words, I think this does follow the algorithm as described. I think the algorithm might just be wrong. So 123 and 666. You pick the larger of the two, right? So this is 666 on the top. This is 121 plus 122 or 123, which is 244. This is 117 plus 121. which is 354 plus 7, 361. All right, and then this is 361 plus 109. It's 470. Yeah, so this seems to be the problem. And then 470 plus 93. And then, so it's 563. And finally, add one more 61. That gives you 624. So yeah, I think each of these cases, right, this is larger, 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 and this is larger. And this is indeed the best possible. So it looks like our algorithm does not give us the right answer when done by hand, which is sad because I thought I was so close. I thought I was doing so well. Oh. Alright, let me lay down for a minute because I'm feeling a little tired here. Feeling just a bit sleepy. Let me think for a moment or two. Oh. What could it be? What could be the problem? Excuse me. What could be the issue? What could it be? What am I looking for here? What are we looking for? Oh, excuse me. Oh man, I'm tired. Huh. I feel like I'm gonna fall asleep here. I might do that. I might, once I finish here, go to take a nap. Excuse me. I'm real tired. I'm exhausted. So what I want to do is Excuse me. Yeah, I'm sorry. I'm just thinking. Mind is wandering a bit. Um, uh, okay, so what do we do? Sorry, excuse me for a minute. I'm kind of, mind is wandering a bit, and I'm also very tired, suddenly very tired. Okay, specifically trying to figure out, right, so this algorithm does not appear to work correctly, right, because the smallest number of those pairs, so the largest of those pairs, 557, is too big. It's not the correct answer. The correct expected answer is 555. So correct answer is 555, and we got 557. Now, I think the answer that we would want to get there, it's very close to 5. It's, I mean, I would think the tree that we would be considering there is very similar or very close to the one that we had that we had considered that got us 557. I want to say, so like we have like something very close to the right idea. It's not quite the right idea, but it's very close. The difference between the correct answer and this answer is that, you know, even though this calculates things a lot more faster, they're not correct, and it looks like maybe we're skipping the root index that we should be choosing. And that might be part of the problem, that there's sort of a slightly different possible root index that we could be choosing. And that would be better, I suppose, I guess, something like that. Let me think about this. We can try to calculate for that particular number, that value. We could try to calculate what, for that particular number, that particular value, we could try to calculate what the correct answer would look like, and see how that relates back to the algorithm that we've got, that we're considering. Yeah, let's do it that way. Let's try to sort that one out. Okay, let's do that. All right, let's give me a moment here. Okay. Oh. All right. So if we were to do this and record, excuse me. so this is the right answer. This is brute force though. What we want to do is record which index. And what we're going to do this. Something like this. Let's see what this does. It's like debug. It's some debug code that's put in here. So let's say have yet another one of these. So 124. We want to say 105. That's interesting. So can you imagine that? 105 being selected rather than 109. So that's very interesting. Right? Somehow we pick 105 and the left side is 106 to 124, or the right side rather is 106 to 124, and the left side is 1 to 104. Yeah, see, that is very different from what we were doing before. And I couldn't really tell you why that is. Yeah, I don't know, actually. I really don't know why this is. It's looking like the brute force way is sort of one of the only ways to do it, or maybe there's a way to prune it or optimize. I don't know. I think I probably could look at the discussion now instead of trying to keep trying to do it this way. But I don't know what 104 is, and I don't know what this, if we recurse on both of these cases, what it looks like. We could try that. Find out what that looks like. Mm-hmm. 104. 106 to 124. This is 104, 1 to 104. And 106 to 124. Okay, let's see how that goes. 424 and 450. 105 gives you 5 529, and 450, 105 gives you 555. So the question is, how do we end up picking that 106 to 124, and how does that give you 450? So it's still the right side that's the larger, but it's somehow the organization of these nodes. How many nodes is there? 124 minus 106. It's 118. And it's inclusive, right? Both edges are inclusive. So we add 1. So there's 119 nodes here. No, excuse me. Did that wrong. There's 19 nodes there. There are 19 nodes there. That gives you 18, but there are 19 nodes total. And the question is, how is it that you organize these 19 nodes and they give you 450 for the worst possible route? That's really interesting. Well, I'm assuming you've got to have the space part 1, 2, 4, 1, 2, 3, and 1, 2, 2, right? So 450 minus 1, 2, 3. Now you're left with this 327. And what's the next part? I have 121 here. $118. $121. I get this 206 somehow. And I would say, I guess you have 117 here. Now, I guess that's the thing, is that you could do a few different possibilities here for the other 117 to 106 to 117. Still 11 nodes. Still a lot of nodes. So 117, and then you've got what is it? There's 3 on the right over here, which would be like 116, 115, and 114. That's like 113. And another 3, 112, 111, and 110. Right? And so then I have 106 to 110. Okay. And what is this so far? 123 plus 121 plus 117 gives you 361 minus 450. So, what happened here? This doesn't seem right, man. So this is somehow 450 on the right side. 117 plus 121 plus 123 minus 450. Somehow we get an 89 over here. This can't be right. There's no way this makes sense. What? There's no way. There's no way that this makes sense. I think this is the only way to do it. What is going on? So confused. Somehow 106 to 124 gives you 450. Oh. Oh. I think I know what the problem is. You don't need to do it this way. You could put more nodes in this left subtree. That's why, because these are not necessarily full binary trees, binary search trees. These could be unbalanced. That's why. Got it. Got it. Now I understand. These don't need to be totally balanced binary search trees. These could be binary search trees, they don't need to be balanced binary search trees. That's the issue. Got it. Okay, understood. Excuse me. You can put over here whatever you want to put. So we said we're going to put these over here in this way. So you have 244, and then we can organize the head node and the head node of that in whatever way we want. We just have to do 450, right? So we can do 123 plus 121 minus 450 is 206. We actually won't be able to do it that way. Let me say 106 to 124. Let's actually do a few routines. So we said test will be set to which index, right? So we'll do 106 to 124 and print test. It's really the root. $117. Yeah. Okay. That's gonna compile error because calculating declaring T2 twice. Wait, what? Okay, I think I know what to do. What? I am so confused. What is going on? 106 to 124, the root is 117. 118 to 124. The root is 117 again? Huh? That's really confusing. What? What? It's probably just programmed incorrectly. I'm kind of like doing some kind of wonky stuff with my tests here. What is going on? Apparently it's 117 again. I don't know how that works. 118 to 124. What's the root node of? I'm trying to find the root node for this guy. I think it's because this is. Oh yeah, that's why. Because it was already calculated, right? Yeah. It's because you just memoize. It just returns directly. That's why. It's got something to do with how I programmed it. Also, we're at like 2 hours now. Look at this. We want to check. Let's do this. Just say memo root. Do it this way. That's fine. I don't even need that anymore either. A lot of debug stuff here. We'll just clear that out later. Okay. See how this goes. Compiler, nice. Nice. Where is that happening? Don't really need to do that, do we? Okay. 117, 121. So 122 to 124. You actually don't really need to do that, do we? Am I crazy? Am I seeing things here? So 106 to 124, 117 is on the right side. 121, 123, 450, 250, 44. Am I nuts? Am I going crazy? 117 plus 121 plus 123 minus 450. So this is balanced on the right side, but it does not contribute the most? Okay, see that's a little weird. Yeah, so the left, that's kind of what I was thinking. The left binary tree is not at all balanced. So this is indeed the root, these are indeed the root nodes, right? But what goes on the left side now, we do 106 to 116, right? I think that's the part that's going to be interesting. It's nice that we have an algorithm that works so we can kind of explore the different pieces. Yeah, this part's interesting. Okay, what does this look like? So 106 to 116 is 113. Wait, what? Yeah, okay. And then what about 106 to 112? $109. 106 to 112 is 109. Yeah, I see that. 109. And so this is going to have 112, 111, and 110. There you go. And now you can do 106 to 109, which is clearly 108, 106, and 107. Which is here, here, and here. There it is. There it is. That makes a lot more sense. So this is not indeed, so indeed you were able to fit more into this tree on the left side. This was not just a simple power of 2, right? Because this is not a balanced binary search tree. That's the key. I think I was saying that before. It's not balanced. The assumption I was making was that it was balanced. So how do we figure that out, though? How do we recognize that, realize that? These are still right, but actually the 450 comes from this guy down here on the left side. 117 plus 113 plus 109 plus 107. Is that right? Oh no. It's 117 plus 113 plus 109 plus 111. There you go. This is actually the largest path to consider, which is interesting because I wasn't expecting that at all. The two things were you can actually you get a better solution by shifting over to the left a bit, by shifting more elements, fitting more elements on the left side, making this tree not a balanced binary search tree, and then putting more elements on the left side, thereby reducing what this recurrence amount would be and slightly increasing what this right side would be, because there's a difference between the recurrence amount on the left and this kind of large sort of right side. You can actually kind of find a middle ground in between by making this a little bit smaller and making this right side a little bit larger. Great. That's interesting. Wow. Yeah. So, okay. Huh. Wow. Well. Forgive me. Forgive me. Mind is wandering all kinds of places. So my algorithm is wrong, which we kind of already knew, but here we are, realizing that, thinking about that. Why and what can we do about it? Well, we know why now. That's what I suspected before. Oh, excuse me. I was confused because I didn't really think about that the path would actually take, would take the left side rather than the right side. Because the right side's kind of small, but the left side you can make a little bit bigger. If you make the left side a little bit bigger, then you make the left subtree. It's get the left side of the right subtree, make that a little bit bigger, unbalanced, and then you could then take the left subtree and make that smaller, which then would bring down your bound a little bit. Which is such an incredibly subtle thing to do. Very slight, but significant thing to do. And if you wanted to have a faster algorithm, you would need to consider cases such as that, scenarios such as that. How do you do that, though? How does one do that, though? Huh. Excuse me. Yeah, I'm still thinking over here, forgive me. Kind of just like wandering around my thoughts. Excuse me, because I don't know how to optimize this and make this faster. At least offhand. I mean, there's got to be something in there with regard to. Okay, I think I know what it is. I want to say. I want to say something like you could. You make this logarithmic jump from the right side, right? Assuming it's a full binary tree. And then there are situations where you could actually use a slightly modified binary tree. Excuse me. But how would you identify those situations? How would you even know those? You could use a linear search, maybe sort of run the algorithm a few times linearly. You know, for the most part, use the logarithmic search, and then use the and then use an iterative search. Actually, that's also logarithmic too. I want to say a logarithmic number of logarithmic searches, if that makes sense. Because you'd kind of like, how many additional layers do you add to your binary search tree? Excuse me. How many additional nodes? You know, you probably don't add that many. I want to say it's probably only at most like one. So I think you still would be logarithmic time even if you added an extra kind of linear search at the end. Yeah. Just thinking how many. I think it is still relatively balanced. I want to say that you really only modify the tree by probably one level of depth, and it's probably only. I want to say it's at most 3 elements, really. I want to say that's probably true. And the reason for that is because you would have to add a whole node again to your path if you increase the depth by more than 1. And it's unlikely that adding another node, like if you could add 2 nodes, then probably you could just add, if you could add 2 nodes, then probably you could add a whole depth of the whole, you know, a new depth of the entire right subtree, search tree. Yeah, I want to say something like that. And yeah. So I think you just add 1 node. Or 1 depth. So we really only have to search like 3 or 4 elements from that point. I want to say. At least that's true when n is 200. I don't know if n gets really large, if that starts to change. I don't know. Excuse me. Yeah, we could add like an extra constant multiplier in there. I do a few extra checks. All right, let's do that. Let's try it. Let's just see. You know what we're gonna do? I want to test to see if we're gonna just write a little. We're gonna print some more debug information, or I'm gonna print some more debug information. And what I'm going to look to do is already 2 hours and 15 minutes. Okay. What I'm going to look to do is print the differences between this sort of calculated value that we expected and then the actual value for this root node. Excuse me, that's what I want to do for a few different test cases. For each test case, we'll say. Excuse me. All right. Yeah, let's do. All right. These don't use the same variables, I think. No, they don't. It's a test instead of ret. Okay. So we want to say expected root expect actual root actual value. Okay, something like this. So yeah, it was a difference of 4. And we'll do let's see how many of these have differences. Oops. Oh, my body. Oh, back of my neck. So basically the difference between this expected root, actual root. So we'll do it this way. Actually, we'll say diff equals the expected minus the actual should always be positive, I think. So if diff is greater than 0, then do the below. Something like this. Okay. Oh. Say if it's not equal to 0. Okay. So once we get to 111, expected root, the actual root. Five, 113. Let's also just print and to 130. Expected root, actual value. So this is a pretty big difference, right? This is a difference of 99 and 111. So I was thinking it was only going to be a difference of like 1 or 2, but this is pretty significant. 100, 112, this is a difference of 12 each of these, looks like. It's pretty far away. This is a difference of 8. A few times. Yeah, 170, that's a difference of 8. This is 4 a few times. This is also 4 for a while. Now, what's also interesting is the expected root and the actual root. Their differences are kind of, it's not necessarily positive or negative. Right, so here it's the expected minus the actual is positive, whereas for these other ones, the expected minus the actual is negative, which is a little strange. So I think that means that I don't actually know what that means. If the expected is 99, but the actual is 111, I suppose that means that that we put too many things into the right subtree if we got 99. Yeah, that's interesting. into the right subtree, and this is on, for this one, it's not enough things are put into the right subtree. These cases. I don't really have too many also. It's 4. Yeah, I mean, pretty interesting. I don't know. I don't actually know how I would solve this more efficiently. I think I need to think about it for a while, try to figure it out. I think we'll go with our original solution, the cubic solution. I don't really have a solid way to kind of hash out those issues where there's a difference of 8, difference of 15, difference of 4. It's not obvious to me exactly how and why those things are. So pretty interesting question. Let's briefly look at the discussion. I think maybe I'll have to come back to this again to really understand the discussion portions. O(n) squared, quite hard. Yeah, wow, okay. Recursion memoization. I have O(n) cubed, yeah. I don't know, maybe we'll come back to this another time. We'll come back to this. Make a part 3, I guess, sometime in the future. I don't know when. But I didn't really get a solid solution to this, I think. There's probably more to it. There's probably a way to kind of finagle this, manipulate it. Like if you notice these differences, they're kind of like consistent for a period of time. You can kind of see it's a difference of 12 between 130 to 140. And then it switches at 130 to 135, and then once it gets to 136, then it switches to a difference of 8, and then that difference of 8 is kind of consistent for a while. So it's not really obvious what to do or what's going on. But it looks like there's some kind of pattern in there that you could probably exploit to make this more efficient. I want to say I think you can do this even faster time, do better than just, I think you can do it better than just cubic time or even quadratic time. My suspicion is you can do even better than quadratic. I think you can do this in like n log n time or linear, possibly even linear time. I don't know if you can do linear, that's maybe kind of pushing it, but let's go back to what we had before. That solution was sufficient, so go keep that. Yeah, we'll keep this one then. Simple solution. Yeah, okay. Okay, so yeah, thank you for watching. I'm going to take a break. Definitely this was like kind of brutal. Not brutal, but like really thought about this a lot, put kind of a lot of time into it. Yeah, thanks again for watching. I will talk to you soon. Gonna go ahead and head off here. I guess the takeaway is that this is a challenging question. I believe there's a more efficient way to do it than what I did, and I may or may not look into that later in the future. What I suspect is that there will be a solution. What I suspect is that there will be a question in the future. That'll be like part 3, the third question, and they're gonna open the constraint on n and make it harder, And then I think that'll be like a hard question. And then I'll have to kind of dig deeper. But I do think there is some kind of pattern in there that could be exploited if you just kind of dig deeper. So probably in the discussions they refer to it somewhere in there. So let me go. Also, I'm just kind of noticing my volume is kind of loud, kind of high. Yeah. All right. Take care.